Welcome to This Explainer. Today, we're going to completely shatter what is arguably the biggest myth in electrical engineering. I'm talking about the zero-volt ground. If you've been designing circuits under the assumption that your ground plane is just this magical, infinite sinkhole where noise simply disappears, well, you're definitely not alone. But it turns out that kind of thinking sets systems up for total failure. We are shifting our mindset away from those theoretical textbook diagrams and diving straight into the physical, messy reality of electromagnetism. Here's our roadmap for today's explainer. We'll cover the zero-volt ground myth, bonding for high frequencies, smart shielding by frequency, defeating cable harness noise, and finally, tools for iterative design. Let's get right to it.
Starting off with Section 1, the zero-volt ground myth.
To get this right, we've got to fundamentally redefine what ground actually is. Ground is not a zero-voltage plane, period. It's really just the reference potential from which a circuit is measured, and crucially, it's the path of least impedance for current returning to its source. You know that concept of an equipotential surface where every single point on a metal plane measures exactly 0 volts? Yeah, that's a total myth. Real structures, no matter how incredibly thick the copper is or how massive the chassis is, always have impedance. And current strictly follows the path of lowest impedance, every time.
Now, because of this ground impedance, which we'll call ZG, something really interesting happens. High currents flowing through shared return paths actually create a voltage lift. It's just basic Ohm's law, right? Voltage equals impedance times current. So imagine a heavy current running through the exact same ground path as a super-sensitive sensor. That ground potential literally rises. The sensor, which is referencing that exact point, mistakenly perceives that lifted ground voltage as noise in its signal. It's not some external interference beaming in, it's entirely self-inflicted noise simply because the ground itself moved.
So how do we fix this? Well, we have to strictly differentiate between our big, bulky power grounds, like your 50 Hz power or heavy DC returns, and our highly sensitive electronics reference grounds. Casually dumping everything into the same chassis ground is a massive, massive risk. Instead, you need dedicated ground returns. That negative reference has to be brought directly back to its intended return point. And sure, yes, this adds a weight penalty in platforms like aircraft, tanks, or ships. But you have to treat it as a totally non-negotiable requirement if you want to keep that sensitive reference shield clean and stable.
Moving right along to Section 2, bonding for high frequencies.
When it comes to the actual geometry of your bond straps, there is one massive, completely non-negotiable number you need to burn into your memory: 5.
This is the famous 5-to-1 rule. Your bond straps must satisfy a 5-to-1 length-to-width ratio. Now, long, thin straps or simple little wires, they work perfectly fine for DC or standard 50 Hz power, but at radio frequencies, it's a completely different ballgame. A thin wire adds massive amounts of inductance at high frequencies, which creates wild resonances. In fact, at RF, a poor bond effectively becomes an open circuit. It secretly turns a beautifully designed but improperly bonded enclosure into an antenna that's just actively radiating EMI everywhere. To stop this, braided bonding straps with that wide, flat geometry are absolutely essential.
Interestingly enough, knowing what not to use for bonding is just as critical. Never, ever rely on mechanical interfaces like shock mounts, nut-bolt contacts, or movable joints for your RF bonding. Look, a standard multimeter might beep and tell you that you've got DC continuity, but DC is completely irrelevant here. Things like grease buildup, a thin layer of paint, or free body motion, think movable parts on a gun system or an industrial robotic arm, will easily degrade that contact. And when that happens, your RF impedance skyrockets and your shield is completely broken. So how do you actually validate a good bond? Well, instead of casual micrometer checks, you should always validate your bonding using the 4-probe method. This is the standard Milstad 464 style check, and what you're targeting is an incredibly low resistance. We're talking right around 15 milliohms measured between the unit body and the nearest platform location. Why the 4-probe method? It's crucial because it completely eliminates the electrical resistance of the test leads themselves, giving you a rock-solid, stable measurement of the actual bond.
All right, Section 3, smart shielding by frequency.
As you can see, the core rules of shielding completely change depending on your frequency. What works flawlessly for a low-frequency sensor can absolutely destroy a high-speed data link. For signals under 1 MHz, and especially below 500 kHz, ground your shield at the source side only. That stops those massive ground loops dead in their tracks. Now, between 1 and 10 MHz, you want to use hybrid grounding. That means one side is terminated directly to ground, and the other side goes through a capacitor or inductor, depending on your noise profile. And for high speeds, anything above 10 MHz, multi-point grounding is the way to go. You ground the shield wherever mathematically possible to keep its electrical length incredibly short relative to the signal wavelength.
The most crucial takeaway here is absolute. An ungrounded shield is basically just a giant capacitor sitting there, waiting to inject noise into your system. Floating metal anywhere near a signal line is incredibly dangerous. It just gathers up ambient noise and capacitively couples it directly into your precious data lines. So, the golden rule here? Never, ever leave a shield floating.
And it's important to remember exactly how to deploy your specific defenses. Twisting your cables is what combats inductive coupling, while physical shielding is what mitigates capacitive noise. Stray capacitance between nearby cables creates noise that just keeps increasing with frequency. So for those highly sensitive or mixed lines, like when you're mixing sensor signals with digital data, twisted shielded pairs are your absolute go-to. They give you that inductive cancellation from the twist, plus the capacitive protection from the shield. It's a total win-win.
Let's dive into Section 4, Defeating Cable Harness Noise.
Believe it or not, the cable-to-cable coupling inside your internal harness is often a way more chaotic EMI environment than any external interference coming from the outside world. You absolutely need a structured approach here. Cables must be physically segregated by their classification. We usually use categories like S1, S2, and S3 based on their sensitivity ranges. Once you've got them classified, you create sub-bundles by function and physically separate them within the main harness. Keeping those parallel runs spaced as far apart as possible drastically reduces crosstalk. And hey, if lines absolutely must intersect, make sure they cross strictly at 90-degree angles. That minimizes the coupling area between the wires.
Now, this segregation doesn't stop at the cables. It extends right into the connector pinning itself. Pin mapping has a massive, undeniable impact on EMI performance. You've got to group those noisy power pins in one region of the connector and completely isolate your sensitive signal pins on the opposite side. And here's a pro tip. If you have spare pins sitting between them, do not just leave them floating. Grounding them allows those spare pins to act as physical electrical shield barriers right inside the connector body. It's a brilliant little defense mechanism.
Also, rather than relying on arbitrary blanket rules for your frequencies, you need to analyze your actual signal characteristics. Sure, pure DC doesn't couple like AC does, but digital switching noise absolutely rides on those DC supply lines. Try using the simple pulse rise time formula. That's 1 over pi times tau. This little equation uncovers the hidden high-frequency components that are secretly lurking in your data lines. Even a seemingly super slow 64 kilobit per second data line can contain incredibly aggressive 10 MHz noise components if the edge rate is sharp enough. The big takeaway? Analyze the rise time, not just the data rate.
Finally, Section 5, Tools for Iterative Design.
Modern electronic routing is basically a maze of complex branching networks and totally unpredictable stray capacitance. Trying to figure out your shielding strategies, coax choices, and physical routing? You really need specialized system-level solvers to accurately predict how the EMI will behave. Software tools like Zuken E3, Siemens Capital, or ePlan are great for handling the heavy lifting of harness architecture. And then you have hardcore electromagnetic solvers like ANSYS, FECO, and CST to simulate the 3D field interactions. They predict exactly how your physical layout will actually perform before a single piece of copper is ever cut.
But here's the harsh reality check. These tools require incredibly precise inputs, things like exact cable sensitivity, precise source and load impedances, and specific sensor levels. And let's be honest, those numbers are notoriously hard to pin down early in a project. So the absolute best engineering approach is an iterative one. Start with a real baseline case. Make standard educated assumptions based on the principles we've discussed today. Run the simulation, learn exactly where the fields are leaking, and then refine your design on the next iteration. It's all about assuming, simulating, learning, and refining.
Which brings us to our final thought for this explainer. It really makes you wonder, doesn't it? Once you finally accept the physical reality of impedance and completely abandon the myth of the 0-volt ground plane, how many other theoretical, textbook assumptions in your current systems need a desperate reality check? The physics literally never lie. Current will always find the path of least impedance. It's your job as the designer to dictate exactly what that path is. Thanks for hanging out with me on this explainer, and I'll catch you on the next one.